This is a stack light, also known as a signal tower light, indicator light, and-on light, warning light, industrial signal light, or tower light. They're used on industrial equipment to signal operational state over large and loud factory floors. Things like, everything A-OK, or my chip bin is full, or I might be on fire. So, what's it doing here, and what does that have to do with discrete math and experimental German television? This is the art of computer programming. It is the masterwork of computer science, written by Donald Knuth starting in the 1960s. It's still unfinished, with only 4 of the planned 6 volumes completed, and the most recent updates from just a few years ago. Famously, he took a few years off from working on it to invent the TeX typesetting engine because he was dissatisfied with the state of computer typography of the day, particularly for laying out equations. More infamously, it uses the assembly language of a fictional mainframe for all the code examples, the wisdom of which continues to be argued to this day. In short, it's the work that everyone in the field knows about, but few have actually read. Well, I'm reading it. Finally. Slowly. It's been a year now and I'm on volume 4B, and I sure wish I'd done this back when the math was still fresh in my head. I can't claim I'm following every proof in detail, but when I see something of interest I dive in deeper. And there is a lot of interest in there. I really do love abstract CS, and the historical nature of a lot of this makes it worth it on its own. For example, in Volume 3, there's an entire lost branch of computer science. It's the study of optimal ways to sort and merge data that spans multiple magnetic tapes. You know, the kind in giant cabinets from back when computers took up entire rooms, storing a couple megabytes each and having to be hand-loaded to be read? Yeah, those. This was already obsolete by the time I started in CS in the 90s, but of course it was a very real problem not that much earlier. Given different memory sizes, read-write capabilities, and rewind speeds, what's the best sorting algorithm? What if you have an external rewinder that can parallelize some of the work? It was important enough at the time that they even dedicated this huge fold-out chart to looking at all the options. In case you've never been exposed, there is little that computer scientists like to get weird about than sorting algorithms. And no, you can't just say quicksort for every situation. I once personally saw a room full of very tired professors and TAs almost get into fistfights looking at a stack of several hundred marked exams needing to be sorted by the student ID written on the front of each one. We ended up using a parallelized version of merge sort, I believe. Anyway, while slow going, I really have been enjoying finding corners I'd never been exposed to before. Like this adorable little algorithm in Volume 2 for calculating powers. It does this by turning as many operations as possible into squaring, which can be a lot faster than simply multiplying a number by itself n times. And it does this through lexical pattern substitution. Take a desired power. Let's follow Knuth here and say x to the 23rd. Write the power in binary as a string, then turn all the 1s into sx, and all the 0s into s. If the resulting string starts with sx, trim it off. Then read through from left to right, squaring the running value when you see an s, and multiplying by the original value on an x. 22 multiplications turns into just 4 squaring operations and 3 multiplications. It's so neat. And the permutations section led me to get a bit obsessed with tower bell change ringing for a bit, resulting with me biking down to Red Square at UW to listen to them practicing on Friday nights. What a wild instrument. The size of a building, can't be played without a whole group of drift-compatible people, and you can't even practice it properly without everyone for half a kilometer all around listening in. He offhandedly mentions this fractally bitwise function, and as always, the complexity that can emerge from seemingly simple equations had me transfixed. I wrote up a tool to generate them, and played with animating what happens as different parameters were changed. This led to an inevitable result once I posted some of the animations, thanks to Colonel Bob, who kindly put up his code for this in GitHub. I was thinking it would be really cool as the pattern on a blanket, and even knit up a test swatch of a 48 by 48 square, but eventually decided the logistics of tracking such a large and unintuitive pattern would just be too annoying. But the one that led me to buying a stack light was the section on gray codes. These are ways to enumerate every possible binary value for a given number of bits, such that they are all visited, with no duplicates, while only changing a single bit at a time. At first glance, it might not be obvious that this is possible. But not only is it possible, it's possible in a bunch of different ways, each with their own interesting properties. It also might not be obvious that it is in any way useful. The classic use case is for rotary encoders. Say you want to know the angular position of a wheel, accurate to 1/16 of a full rotation, or 22.5 degrees. You could use 4 optical sensors, and attach a disk that has 4 concentric circles broken into black and white sections for the sensors to read. A simple binary encoding will give a unique 4-bit value for each of the 16 sectors, so we'll always be able to know which sector we're in based on that value. And that works fine, except what happens when an encoder happens to be positioned directly above a transition from light to dark, so that half of its field is white and half is black? Its reading will be indeterminate, giving either a 1 or a 0 depending on the lighting and how clean the disk is and 1,000 other things. And that's a big problem with the naive binary encoding, because look at this point. Between sectors 15 and 0, all the encoders will simultaneously be transitioning from dark to light. At that point, the system completely fails, with any of the 16 possible readings all equally likely. Max pause error. Enter a gray code. Same setup, but the encoder wheel layout has changed. Now, only a single track ever starts or ends at a single location. This solves the problem seen before, and means that the maximum uncertainty is only ever between 2 neighboring sectors. Which, fair enough, I think that's actually a totally legitimate response when transitioning from one sector to the next. If you want more precision, you'll just have to add more sensors and more tracks. As is often the case, others had actually explored the idea previously, and even received a patent containing the same system. But in 1947, Frank Gray submitted his own patent including the idea, unaware of the prior work. For whatever reason, we ended up naming them after him. But not being ridiculously vain, he just called his system a reflected binary code, because of how they are generated. This can be done recursively for n bits by taking 2 copies of the codes for n-1 bits. The new copy is reversed, then the first set gets a 0 preprinted to each of them, and the second gets 1s. Hence the name, it's literally reflected binary. So as long as you can remember 0, 1 is the base case, you can generate the reflected codes for any number of bits by applying this rule recursively. And this is what defines that pattern of tracks we saw before. And in fact, you can find lots of encoding wheels which use this exact system. It really does get used. And it gets even better, because you can directly calculate the gray code for any binary value by XORing it with itself shifted right by 1 bit. So for 101010, you would bit shift right by 1 to get 010101. Then that would be XORed with the original value to get 111111. Easy. There sure is nothing like having a nice closed form solution for something. This is all supremely neat stuff, and I have no idea how I got so far in life without being exposed to it already. I mean, I had seen encoding wheels, of course, I just had never put any thought into the layout. So I wanted to do some art with the ideas, just to help spread the good news. Some industrial art, obviously. Enter the stack light. After scouring auctions for a few days, I found this 12-volt 5-tier model selling new for less than most of the used ones. I would have liked one with more than 5 tiers, but most start to repeat colors at that point and also get a lot more expensive. Wiring it was very simple. Just connect ground and put 12 volts on the lines for whatever lights you want on. I grabbed an 8-channel relay module for this, which was ridiculously overkill, but I thought the analog clicking of the relays would be a nice sensory touch. Plus I anachronistically imprinted on Forbidden Planet in the 80s, with the weird result that this sound still feels kinda futuristic to me. So that's great, but I wanted to do more. Luckily there are a bunch of other variants of gray codes to explore, but first I was going to need some kind of enclosure for the electronics. Something industrial and solid. I was thinking it would make a nicely interactive piece to have at the booth at OpenSauce. Something younger kids could wail on without any chance of breaking it. Don't get me wrong, kids at OpenSauce are mostly great and I'm really glad they're there, but there are always a couple that could use a bit more supervision. This time watching the auctions paid off, and I scored this lovely old control panel, complete with 6 indestructible Allen Bradley push buttons. 1 for straight binary, 1 for reflected binary, leaving 4 buttons for other gray codes. Perfect. At first I was just going to leave the original button labels alone, wanting it all to come from the same vintage. But I decided that having them labeled stop and start would be confusing and counter to the vaguely educational goals of the project. Getting custom nameplates made would be annoyingly expensive through serious industrial suppliers, but it turns out you can also get it done on Etsy for like 1/10 the cost. I also picked up an emergency stop and a speed potentiometer, both designed to mount in this kind of control panel, which meant they looked right and were also very unlikely to be broken by even the least supervised of children. To mount the stack light, I used basic iron plumbing fittings. The flange was bolted to the back of the control panel, and then I welded the elbow to it to make sure the vertical mast would stay perfectly vertical. I left the mast just loosely screwed in though, so it could be removed for transport. I plan to make a longer one for open sauce, so it'll stick up above the dividers between booths, but this shorter one is fine for now. Getting the stack light to actually mount on the mast was a bit annoying, as there was no indication what the thread on its base was. I eventually figured out it was M16 by 1.5, and picked up a die for that. 3/8" pipe is pretty close, and a lot more available around here, so I turned down the end of some of that to 16mm and threaded it. I have got to be a bit careful when screwing on the stack light not to cross-thread it, as the sharp steel threads I cut would chew up the soft plastic ones without even trying, but otherwise it works well. Wiring wasn't too hard, just the hassle of mounting all the components inside first. I also enlarged the existing hole in the side for a power socket with a built-in switch. There wasn't a good way to mount it to the mill though, causing enough chatter to break the 1/4" end mill I was using. Whoops. But I was able to finish it up well enough with a hand file. I decided to keep the terminal block that came inside the control panel, as it will provide a convenient way to attach and detach the stack light wires. That way I can disconnect them fairly easily when I remove the mast for transport. Full disclosure, the e-stop is not actually wired up as a real e-stop. All it does is change the state of an input to the Arduino. A real e-stop isn't just another button monitored by software that may or may not be listening. It's something that cuts power to everything, forcing an immediate and totally reliable stop to action. But it's not like this is an escalator or some other scary mechanical device with the power to remove limbs, so... The speed control does what you would expect, changing the delay between each loop iteration in the code. I expect I'll be constantly turning it back down after people leave it running at full speed. And that was it, a refreshingly simple build. Let's look at the gray codes available. First we have straight binary, counting from 00000 all the way up to 11111. This isn't actually a gray code of course, but I thought it was important to include for pedagogical purposes. And there is just something very pleasing about watching binary values roll over like a supercondensed odometer. Next, reflected binary, the OG gray code itself. This achieves the basic goal of visiting every value without repeats and only changing a single bit at a time, with of course the added benefit of having a closed form solution. All the other codes on this device are the result of search efforts, and aren't actually algorithms per se. Balanced. A balanced gray code is one where each bit flips the same number of times throughout the sequence. This could be useful for evenly distributing wear if applied to something with a limited number of lifetime cycles. Single track. This is a variant of the basic idea for rotary encoders, but instead of having all the sensors bunched together reading multiple tracks, this uses sensors spaced around the circumference, all reading a single track. If you want an excuse, maybe it's an application which only has room for a single track on the encoder wheel. The one in the animation would provide 12-degree resolution, and is the equivalent of the one visualized on the stack light. But for a more extreme example, check out this 9-bit one on Wikipedia that would give 1 degree of resolution. These patterns were long thought impossible except in trivial examples, but in another patent surprise, Bruce Spedding published several in 1994, apparently not aware of any of the previous work done on the problem. Long run. This one tries to maximize the duration between changes to each bit. I'm not sure if there's a practical application for this. You could probably invent a contrived scenario to justify it, but either way it's interesting. And finally, we get to the one labeled Beckett. Now I know some of you smartasses in the audience are thinking, oh, like Samuel Beckett the playwright? And unironically, yes, like Samuel Beckett the playwright. In 1981, he wrote an experimental play for German television called Quad, in which 4 actors walk around the stage in fixed patterns, entering and leaving the stage at different times. It's oddly mesmerizing, and I generally recommend watching the full thing. Beckett wanted every possible subset of the 4 actors to be on the stage at some point, with only one entering or leaving at a time. That is, he wanted to use a 4-bit gray code, even if that isn't how he would have expressed it. Except, he also wanted to arrange it such that the actor leaving was always the one who had been on stage the longest. The play doesn't actually quite achieve this though, as he was unable to work out such a sequence. Later academic research showed he was right to give up. It simply doesn't exist for 4 bits. Beckett codes might exist for larger ones, but are only currently known to exist for 2, 5, 6, 7, and 8 bits. Luckily, as a Beckett code for 5-bit exists, I could include it on this device. And that's the gray device. It was a quick little project, but I really do enjoy making abstract math a bit more tangible like this. Progress on the modular Conway's life cells is going well, waiting for the third and hopefully final round of prototype PCBs at this point. And the homemade magnetic pogo pin connectors are starting to come together. Printing all the magnet holders is going to be a pain, but I plan on making 150 cells, each with 8 connectors. You've really got to fight for every possible savings at that scale. And I just received this intriguing vertical record player in the mail for a project I'm not going to tell you about quite yet. Sorry, you'll just have to stay tuned for that one. Anyway, cheers.